Hello, this is T Chapman 500, and this is the restored demo CPU. Now, I made this restored demo CPU in Logisim Evolution Holy Cross Edition, and as a result, we don't have a reset input for the RAM. So I made this component to clear the RAM out. What it does is it basically disables input from here and replaces it with its own input. So if we push this button while the clock is running, this thing will be cleared after a few seconds. Let me demonstrate that. Set the frequency to maximum setting. Enable ticks. Right now this thing's running the Fibonacci program. So if I were to hit this, it goes through the RAM and clears everything. Let's reload Fibonacci. There we go. Now it's running at maximum speed, but we are going to slow that down. Reset. So the registers are loaded. And I've set the clock to run at 1 Hz, which is half what's displayed here because this thing simulates half a clock cycle per tick. So what's going to happen is when this number gets too high, it's just going to reset and start over. So we'll let this run for a few minutes. Actually, I think I'll just let it run real time until it overflows. And then I'll show you what the program looks like. Oh, and it overflowed. And now it's resetting. So, let me go into Notepad. Actually, let's go to GitHub instead. So, Fibonacci, check out the assembly file. The changes I've made to the control unit. We have the instruction decoder here, and there is no preloader or anything like that. So the instruction is decoded here, and the decoded instructions are individual lines here, which go to essentially just a series of AND gates. There is a delay built into the system where necessary to make sure that all the timings work out. And the signal generator, which is essentially this block here, is just a series of AND gates. If we go into this, which loads the temporary address register, we can see again a series of AND gates with a couple other types of gates, including a built-in delay. So if we go inside the stepper, we can see that it's much simpler than the previous one. So most of the time, the stepper will be reset on this step. So the moment this thing goes high, a signal is sent to reset this, which sends this thing high and this thing low so quickly that you can't actually see it. Otherwise, the reset signal is going to be on this, and this will go high then low so quickly that you won't be able to see it. And if we go down here to the conditional jump, we can see that rather than having an allow jump signal, we simply have a load and set program counter, and when this thing isn't enabled, none of the gates active. But as you might have seen there, the enable signal did go active. There we go again, and that's just to make sure that none of these gates go on inadvertently. So when this signal is active and the jump condition is met, these will go active at various points in the clock signal. And again, this is basically just a series of AND gates, although I can replace this with NAND gates and replace this with a NAND gate. And if we go back to here, go back to the arithmetic logic unit, I've kind of tidied up the flag decoder and flag selector logic. So we now have a couple of multiplexers and demultiplexers, basically a pair, selecting which part of the flags register to send these flags to. We also can outright disable these things and use this one instead to send flags to the flags register. If we take a look here, we can see that the program counter, if it's going to be incremented, is only incremented by 1. We do not have any logic to store an address ahead of the program counter. What happens is when we load the temporary address register, we keep incrementing the program counter as we load the address register, and then when we finally load the data or store the data, the program counter is at the correct value to retrieve the next instruction. So we don't need a temporary spot to store the address of the program counter to. Instead, we simply multiplex the program counter with the temporary address register. Let's take a look at the register block. We have the data in and data out. Now, because of the limitations of Logisim Evolution, I have to use 2 pins for this. I can't use a single bidirectional pin because those don't exist in Logisim. Now, the reason that this stepper is so different from what I showed in previous videos is because it's faster. Everything happens every single Logisim tick. So every single simulation tick, something happens, whereas before there would essentially be unused ticks. So this allows the simulation to run faster. And of course that does mean that the logic for here does change quite a bit so that we don't get erroneous signals, but the result is exactly the same as before. By the way, you can find this CPU on GitHub at the link that's on the screen and in the description. Also, I hope you enjoyed the video. Please leave a like if you did. Don't forget to subscribe for more and check out the gaming channel for gaming related content. If you would like to support this channel, you can do so via Patreon, PayPal, or Subscribestar. Links are also in the description. Also, I am not sure if I am going to enhance this CPU, although I do have a branch for that. Anyways, this is T Chapman 500 signing off.